Hello there. In this video we are going to discuss detailed solutions of all the questions those are appeared in GATE 2014 set 3 with respect to analog circuit. These are the question numbers you can find in GATE 2014 set 3 paper pertaining to this analog circuit. We will discuss solution detail of each and every question one by one. First question is question number 11. In this question, we have to find out what is the characteristics of a transconductance amplifier. In the previous year solution also we have discussed this question several times, and here again we can analyze once more. The transconductance is nothing but voltage to current amplifier. The transconductance amplifier is nothing but voltage to current amplifier, and the transconductance gain is given by output current divided by the input voltage. If you draw the circuit of a transconductance amplifier, that is, it can be represented as a voltage dependent current source, and here is the input voltage that will be applied. Okay, now we will connect load and source voltage. Source voltage will have some internal resistance, that is Rs, and a load RL will be connected. We will see what will be the overall transconductance and how the characteristics of transconductance amplifier should be. So this is basically the transconductance. This is basically the transconductance amplifier. So overall transconductance gain is nothing but the output current divided by the source voltage, that is Vs. For an ideal transconductance amplifier, it should be such that the arrangement should be such that the overall transconductance gain must be equal to or very close to that of transconductance factor or transconductance gain of the transconductance amplifier. So G has to be equal to this G0, which is equal to I0 by Vs. Hence we can get I0 to be equal to GVs for the transconductance to be ideal. I0 to be equal to GVs for an ideal transconductance amplifier. Okay. Now if we apply current division rule here, then we can get what is I0 current in terms of this current that is GV in. So GV in into R0 divided by RL plus R0. This is the output current. Now this V in we have to find out in terms of Vs. Okay, so we will apply voltage division rule across these two series resistance. So we will get the V into V, Vs into Rin divided by Rs plus Rin. So if we substitute this V in here, then I0 is equal to GVs into Rin by Rs plus Rin into R0 by RL plus R0. So for an ideal transconductance amplifier, we have the required condition, that is I0 should be equal to GVs. For I0 to be equal to GVs, these two factors should be close to unity. If Rin is very greater than Rs, then Rs can be neglected, so denominator and numerator can be cancelled, so this factor can be 1. Similarly here also, if RL is very less than R0 or R0 is very greater than RL, then in that case also this factor will also approximate towards unity. So for I0 to be equal to GVs, this factor has to be equal to 1, this factor has to be very close to 1. For this to become 1, these are the two conditions, that is the input impedance or input resistance should be very high and the output resistance also should be very high. So both input and output impedance or both input and output resistance should be very high. So if we see among the option A, that is high input resistance and high output resistance are the desirable characteristics of a transconductance amplifier. Thank you. Next question is question number 12. In this question, if you see one PNP transistor is given, its VV magnitude value, that is 0.7, or VEB is equal to 0.7 volt, and this beta value is also given for the transistor to be 50, base resistance, that is RB, is given 100 kilo ohm. For V output to be 5 volt, what is the value of RC, that we have to find out. Okay. If we name the terminal, this is base, this is collector, this is emitter, and VEB is equal to 0.7 volt. Okay. Or if we write in terms of VBE, it should be minus 0.7 volt. In the question it is given in the magnitude form. Okay. So here VEB is equal to 0.7 volt. Now if we apply KVL across this loop, let's say IV current is flowing through this resistor RB, then we can have the KVL equation VEE minus VEB minus IBRB equal to 0. Okay. We have V value, VEB value we have, RB value is also given 100 kilo ohm. So you can easily get what is the value of IB from this equation. So IB is nothing but 9.3 divided by 100 milliampere. Okay. From this beta value is also given, so we can get what is the value of IC here. So IC is equal to beta IB, that will be 50 into 9.3 divided by 100, that will give us 4.65 milliampere is the IC current. Now V output voltage is given, we have to find out what is the value of RC. V output voltage is given to be 5 volt, so V output is nothing but IC into RC. Okay, V output is nothing but IC into RC. We have V output, we have IC, then we can easily get what is the value of RC. RC is equal to 5 divided by this IC current, that will give us 1.075 kilo ohm. That is RC value is 1.075 kilo ohm. Okay, thank you. Next question is about a half wave rectifier with capacitor filter circuit, and here it is given that the diode is ideal. We have to find out what is the average steady state current that flow through the diode approximately, we have to find out. Okay. So if this is the input, okay, it has the magnitude Vm which is equal to 10, okay, and its frequency is 50 Hz is given. Okay. As the diode is ideal, we will analyze the circuit during the positive half cycle. As the diode is ideal, so its resistance, forward resistance RF will be 0. So this charging time RC, this charging time RF into C will be very close to 0. So capacitor will charge according to the input voltage. Okay. So the same charging of the capacitor will continue till the input voltage is reaching towards Vm. Okay. So like that the capacitor voltage will charge up to Vm, that is if up to omega t equal to pi by 2, the charge, the capacitor will follow the input voltage. Okay. Then after this what will happen? After this the capacitor will have the voltage of Vm. Okay. And this voltage, that is the input voltage, is continuously dropping than this Vm voltage. So diode will get reverse bias. Okay. When the diode is reverse bias, this will be open. Now the capacitor will try to discharge through this resistor Re. Now discharging time is nothing but RC. RC is the discharging time constant, that will be 400 millisecond, which is very greater than 1 by t. If you see 1 by 50 is nothing but 20 millisecond. So as 200 millisecond is very greater than 20 milliseconds, so the discharging rate is very slow. Okay. Or if you see this RC is very large, then the discharging of the capacitor will be very slow. So it will discharge like that. Okay. Once again, when the input voltage at this anode of the diode increases than the cathode of the diode, then again the capacitor will start charging. Okay. So up to Vm again the capacitor will start charging and again discharge, and it will continue like that. Okay. So during steady state the capacitor voltage will swing between these two levels. Okay. Between these two levels it will swing. The capacitor voltage or the output voltage will swing between these two levels, which will be almost a triangular form. Okay. The discharging time will be very large and the charging time will be very small. The discharging time will be almost equal to that of the time period of the input signal. Okay. Now if we draw the diode current, what will be the diode current? The diode current will occur when the diode is forward bias. So the forward bias condition is this region and this region. During this period only the capacitor will start to charge and the diode is forward bias. So the ID current, that is diode current, will flow. Okay, gradually it will decrease to 0, and same way this ID current will flow. If we average this ID current over the time period T, then we will get the DC value of the diode current, that is the IDC is the DC value of the diode current. Okay. Now if we see what is the DC value of the output voltage, DC value of the output voltage is nothing but the DC value of the average value of these two levels, or the average will be coming around the middle of this, which will be equal to Vm minus, suppose this swing is, total swing is VR, then Vm minus VR by 2 will be the DC voltage. So VDC voltage is nothing but Vm minus VR is the total swing divided by 2. That will give us the DC value or average value at the output side or at the output voltage. Okay. Similarly, now we will try to find out what is VR, this peak to peak swing of the output voltage. So the charging time, during the charging time of the capacitor, the charge stored in the capacitor will be equal to C into VR, that is the voltage VR, C into VR, and during the discharging time, this IDC current, that is, we have assumed that this averaging is over the whole period, so we can take IDC current as the discharging current. IDC into T will be the discharging charge from the capacitor. So this will be equal to this IDC into T. T is the time period of the input signal. Okay. So from this we can get what is the value of VR. VR will be equal to IDC divided by C into F. F is nothing but the 50 Hz, that is the input frequency. Okay. So if we will substitute this here, then we can get this expression VDC is equal to Vm minus IDC by 2 CF. Okay. Now VDC is nothing but the average value of the IDC current flowing through this resistor R. Okay. So VDC is nothing but IDC into R. Okay. Now we will equate these two. So we can easily get what is IDC. IDC is nothing but Vm divided by R. R is given 100 ohm divided by 1 plus 2 CF. 1 plus 2 CF is nothing but C is given 4 millifarad. F is 50 Hz. After putting this, we can easily get what is the average value of the diode current. That will be approximately equal to 0.0976 ampere, and it is asked in the ampere. So this is the current, that is the DC value of the current is 0.0976 ampere. Thank you. Next question is question number 37. In this question, a transistor, BJT transistor is given in the common emitter configuration. Beta value is given, VB value is given, saturation voltage VC SAT is given to be 0.2. We have to find out among the option which one is correct. That is, we have to find out RC value and its corresponding region of operation of the BJT. We have to find out the region of operation when RC is varying. Different value of RC is given, we have to find out the region of operation accordingly. So let us apply KVL across this loop, then we can get 5 minus IB into RB minus VB is equal to 0. From this we can easily get what is the value of IB. IB is nothing but 4.3 divided by 50 milliampere. Okay. Then from this beta value is also given, so we will get the IC value to be 4.3 milliampere. Suppose here the voltage is VC, here the voltage is VC, then VC is nothing but 10 minus IC into RC. Okay, which is nothing but VCE, because V voltage is 0, so VC is nothing but VCE. So that is equal to VC. Now when VC value is greater than 0.2 volt, then the transistor is in linear region, because when VC value is 0.2 volt, then it is in saturation region. So this is the condition. Otherwise, if VC is falling below 0.2 volt, then VC will be maintained at VC sat, that is 0.2, and the transistor will be in saturation region. Okay. Now for the transistor to be in linear region, we have to find out the condition by putting this VC value to be greater than 0.2. VC is nothing but 10 minus IC RC. Okay. After solving this, we will get this expression, and IC value we know. So from this we will get, if RC value is less than 2.28 kilo ohm, then the transistor will be in linear region. Okay, the transistor will be in linear region according to this condition. And if the sign is changed, that is this RC is greater than equal to 2.28 kilo ohm value, then the transistor will be in saturation region. So we have these two conditions. Based upon these two conditions, we can find out what is the exact solution among the option given. So if you see the first option, RC is 1 kilo ohm, which is less than 2.28. So BJT has to be in linear region, but it is given in saturation region. So this option is not correct. Coming to the second option, RC is equal to 3 kilo ohm. So greater than this one, the transistor should be operating in the saturation region, and the transistor is operating in the saturation region as per the condition. So B can be correct. Coming to the option C and D. In the C and D, the RC value is greater than this 2.2 kilo ohm. So the transistor has to be in saturation region. But here in the option it is given in the cut-off region and in the linear region. So these two options are also not correct. Hence option B is the correct answer. Thank you. Next question is question number 38. We have to find out the output voltage expression in terms of the input voltage V2 and V1. Among the options, which one is correct, we will see. If you see here, the transistor is, there is a negative feedback. Because of the negative feedback is there, so the op-amp will always act as an amplifier. It will never saturate. So virtual ground concept will appear here. Suppose V is the voltage here, so V will be equal to V2 as the op-amp is ideal, and it is acting in the amplifying region. So the virtual ground concept we can apply, that is V2 is equal to V. Now we will apply KCL at this node. If we apply KCL at the node V, then we can write this V1 minus V divided by R plus 0 minus V divided by 2R plus V0 minus V divided by 3R. That will be sum total of all current at this node will be equal to 0. Okay. So after solving this, we will get this V output in terms of this V and V1. Okay, V output is equal to 11 by 2 V minus 3 V1. This V is nothing but V2 because of the virtual ground concept. So V output is equal to 11 by 2 V2 minus 3 V1. So we have V output is equal to 11 by 2 V2 minus 3 V1. Among the option, if we see, this one is the solution. So minus 3 V1 plus 11 by 2 V2 is the correct answer. Hence option D is the correct answer. Thank you. Next question is question number 39. In this question, a MOS, that is NMOS is given. Okay, its W by L is given, VDD value is also given, mu and COX is given 100 microampere per volt square. Threshold voltage of the transistor is also given 0.5 volt. The transistor, it is further given that the transistor switches from saturation region to linear region. That is just when VDS is equal to VGS minus VT. Okay, that condition leads to the transition between saturation to linear region. Then in that case, what is the value of the input voltage, that we have to find out. Okay. So if you term this as drain, this as gate, this as source, according to this MOS, okay, then at the transition, as I said, VDS should be equal to VGS minus VT. Okay, because if VDS is greater than this value, then it will be in saturation region. If VDS is less than this value, it will be in simply linear region. Okay. Now VGS minus VT, VGS is nothing but V in minus 0, that is V in minus 0.5 volt is given VDS. So VDS is equal to V in minus 0.5 volt. Then as it is switching from the just switching from the saturation region to the linear region, we can apply the saturation current equation ID. Mu, that is ID equal to mu n CoX W by 2L VGS minus VT whole square. After putting this value, we will get the ID current to be 0.1 VDS square, that is in milliampere. VDS square, why? Because V in minus 0.5 is nothing but VDS. Okay, so this is the ID current. Now this V output is nothing but the VDS, because VDS is 0, so VD is nothing but VS. V output is nothing but VDS, and VDS is nothing but VDD minus IDR. IDR, R is given 10 kilo and ID is this one. So if we substitute this ID here, then we will get a quadratic equation of VDS. If we solve, we will have two value of VDS. One is negative value and another is positive value. For this question, VDS has to be positive. So if we take the positive value, it will be 3 minus 1, which is equal to 2 by 2 equal to 1 volt. So VDS has to be 1 volt. Okay. Then if VDS is equal to 1 volt, from this we can get what is the value of Vin. Vin is equal to VDS plus 0.5 and VDS is equal to 1 volt. So Vin will be 1.5 volt. So this is the required answer. So Vin is equal to 1.5 volt. This concludes analysis of all the questions those were appeared in GATE 2014 set 3 paper. Okay. If any question is missing or any questions are missing, please let me know so that those questions also can be added in this part. If you have any query or suggestions, please let me know. I will be happy to address your query. See you in the next lecture. Until then, stay safe, stay healthy, keep believing in yourself, and most importantly, keep preparing harder and harder. Thank you.